If we repeat this, but without shock, let me do something here. Just I wrote it here. It will end up to this huge shape. This is the integration. This is the integration. But now each term here, it is integral. If you can see, each term here is integral. This is over gamma 1, gamma 2, gamma 3, gamma 4. This is for each, this is for xi1, this is for xi2, this is for xi3, this is for xi4. And this is the boundary condition here. This is unknown boundary condition, this is known boundary condition. So you will end up to H times U equal to G times T. Part here is known, like this one. These parts are unknown. And part here are known. This one is unknown. This is known. This is known. So you will be able to directly compute the unknown parts for the displacement on the boundary or the tractions on the boundary. Here is the displacement are the unknowns, and this is the traction on the boundaries. Directly, without phi. No longer I have phi. This is because of that we call it the direct integral equation. Still until now, wrapping up again, in part 1 of the lecture, we talked about boundary only or boundary domain method. We saw 3 types of domain integrals. Still another type of domain integral is called the stiffness type domain integrals. I'm going to cover it when I talk about the stiffness formulation. Okay? And we saw how to play with the differential operator I have and with the fundamental, the associated fundamental solution. In the second part of the lecture, we covered elasticity equation. Elasticity integral equations, whether it is indirect or it is direct. We covered also, we have whether it is regular or it is singular. And we had some essence about what is the meaning by hypersingular integral equation. In the indirect, we could have discrete or we could have continuous. The discrete version, it is the method of fundamental solution. Okay? So we could have discrete version of the indirect version. In the direct version, it's very difficult to have discrete version. We can compute the integrals instead on boundary, you can compute it on boundary points. The first guy who did this one is Subrata Mukherjee, who did it with called the boundary node method. What we covered it is the integral forms, is not the elasticity equation. So we need to cover the elasticity equations to see from displacement how to compute strains, how to compute stresses, how to compute tractions. I hope I give huge information today, and I hope you followed me up with this information. Thank you for listening, and I am ready for questions.
Hey, thanks for your teaching. Yeah. So thanks for
Mr. Ibrahim with us. He's going to make a perfect montage for these lectures and cut it to small parts, and they will send it to you.
Yeah.
Okay.
Yeah.
No
that's why interesting. Yeah. Any questions? I think the potential problem is the basic problem, and as we see that's one big picture. So the elasticity problems is a little bit complicated. Yeah.
Actually,
this is 2D.
We can formulate elasticity as potential problems because every when we talk about fundamental solution, we can decompose any fundamental solution to small potentials. Then we can formulate our problem in terms of these potentials. As far as we formulate this potential, it will be totally potential problem. But the problem we have is the prescribed boundary conditions in terms of the potentials. How can we formulate this? This is the main problem. We'll talk about this also when we talk about advanced formulation.
Okay. Yeah.
We'll cover everything. Believe me, we will cover everything. But the problem is to have the spirit of learning. Because actually, once you dedicate yourself to boundary elements, you have to leave everything nearby. With boundary elements, you have everything. Forget about all other stuff. You can formulate everything inside boundary elements.
Mm-hmm. Yeah.
And actually, it is tasty. In boundary elements, it's tasty. So you'll enjoy every day.
Enjoy every
Okay.
every week. Yeah. Yeah.
Yes. Okay.
So
Now, no more questions, so I have to say goodbye now. If there is no more questions.
yeah, if no, anyone.
So
If
unmute
no,
yourself and ask direct.
Yeah.
Okay. No more questions.
Yeah.
No more questions. So Professor
Yeah.
Fu, I have to say goodbye now. See you next week.
Yes. Thanks for your teaching and thanks all you participating. And see you all next week. Yeah.
Thank you.
Okay.
Bye.
Okay. Bye bye.
Bye.
Bye bye.